Alright, PreCalc, here we are with 4.1, radians and degrees. Okay, probably something that we should be familiar with by now, degrees at least, and then maybe a little bit of work with radians last year in Algebra 2. Alright, we're measuring angles. Starting position of a ray is called your initial side of the angle, and the position after rotation is called your terminal side. Usually it's more like this. Over here, we're used to thinking about it on the XY scale, initial side rotating to terminal side. The end point of the ray is the vertex of the angle. This perception of an angle fits a coordinate system in which the origin is the vertex, and the initial side coincides with the positive x-axis. Such an angle is said to be in standard position. Positive angles are generated by counterclockwise rotation, so going up this way. And a negative angle is going to rotate clockwise. Angles are labeled with Greek letters, alpha, beta, and theta, as well as uppercase letters A, B, C. In the figures at right, note that alpha and beta have the same initial and terminal side. Okay? So alpha is taking the short way here, the positive rotation, and beta goes the long road. Well, I guess it goes the other way too. It just goes more than 360. So it's going to go this way as well. They both start here, and they both finish there. So they are said to be coterminal. This one, alpha goes the positive route, and beta goes the negative route, and they both end over here. Coterminal there as well. Radians. The measure of an angle is determined by the amount of rotation from the initial side to the terminal side. One way to measure the angle is in radians. This type of measure is especially useful in calculus, and this is pre-calculus, so we're going to be using radians quite a bit. To define a radian, you can use the central angle of a circle, one whose vertex is the center of the circle, as shown in the figure. Arc length is equal to radius when your rotation equals 1 radian. So 1 radian is the amount of rotation needed to make your arc length equal to your radius. 1 radian is the measure of a central angle theta that intercepts an arc length s equal in length to the radius r of the circle. So that's kind of how it kind of came to be. So theta is arc length divided by radius. Because the circumference of a circle is given in 2 pi r, if we substitute 2 pi r in there for s, you'll notice that the r's cancel out, and that theta would just be 2 pi. And that's how we get 1 full rotation is equal to 2 pi. And then from there you can build up all your little fractions. A half of a revolution, or 180 degrees, is going to be pi. A fourth of a revolution, 90 degrees, is pi over 2. There's all your fractions of it. Hopefully the voice holds out here. Alright, recall the 4 quadrants in a coordinate system. Quadrant 1, 2, 3, 4, going counterclockwise. The figure shows which angles between 0 and 2 pi lie in each of the 4 quadrants. So we're probably pretty used to thinking about that in 0, 90, 180, 270, 360, and breaking it up like that. And now we're thinking about it in terms of pi. 0, pi over 2, pi, 3 pi over 2, and back to 2 pi, or 0. 2 angles are coterminal if they have the same initial and terminal sides. 0 and 2 pi are coterminal, as are pi over 6 and 13 pi over 6. 13 pi over 6 is the same ending spot, just with you go around the circle more than once. Finding coterminal angles. Alright, took us a while, but here's our example. So, in degrees, you're probably used to just adding or subtracting 360, okay? With radians, we're going to be adding and subtracting integer values of 2 pi. It'd be about the same thing. So, for a positive angle 13 pi over 6, we would subtract 2 pi, or 2 pi rewritten in a friendlier version here would be 12 pi over 6. That way it's already got a common denominator. So 13 pi over 6 minus 2 pi. We're going to change that to 12 pi over 6 so that it matches. 13 pi over 6 minus 12 pi over 6 would be 1 pi over 6. For the positive angle, 3 pi over 4, you could subtract, again, we're going to subtract 2 pi, but let's make that a friendly version of it. We're going to subtract 8 pi over 4. Subtracting 8 pi over 4 leaves us with negative 5 pi over 4. And that's what I've got pictured there for us. For the negative angle, negative 2 pi over 3, we could add 2 pi, make it friendly. 2 pi and written in thirds would be 6 pi over 3. So negative 2 pi over 3 plus 6 pi over 3 would be 4 pi over 3. Alright, these all came out in to amounts that did not need to be reduced. So if you did need to reduce, make sure we get that done. Degrees. The second way to measure angles is in terms of degrees, denoted by the symbol, little degree symbol there, whatever you want to call it. 1 degree is equivalent to a rotation of 1/360th of a complete revolution. To measure angles, it's convenient to mark degrees on the circumference of a circle as shown below. Okay, we know all this stuff here. 360 is a full circle, a half one is 180, a quarter is 90. Okay? Because 2 pi radians corresponds to 1 complete revolution and 360 degrees corresponds to 1 complete revolution, we come up with the equation, I guess, your formula to change back and forth, that pi equals 180 degrees. Pi radians equals 180 degrees. Okay? So if you have degrees, you're going to multiply by pi, divide by 180, and reduce. Reduce your degrees over 180. If they give you radians, you're going to multiply by 180 and divide by pi. Usually there's a pi in your radian measure, and then the pi's would cancel out. Sometimes it's not, and then you're going to have an ugly answer. Okay, to convert degrees to radians, multiply the degrees by pi over 180. To convert radians to degrees, multiply the radians by 180 over pi. Alright, converting degrees to radians. Let's see what we got. So we got 135 degrees times pi over 180 degrees. Okay, 135 over 180 will reduce to 3/4, and then you still have your pi, 3 pi over 4. 540 degrees times pi over 180. Okay, degree signs cancel out. 540 divided by 180 is going to be 3. Tack on the pi radians. Negative 270 times pi over 180. 270 over 180 That's going to be negative 3/2. Put the pi on the back. Negative 3 pi over 2. Changing radians to degrees. Okay, you got pi over 6. Let's times by 180 degrees over pi. Pi's cancel out. 180 over 6 reduces to 30 degrees. 5 pi over 3 times 180 over pi. Pi's cancel out. Okay, I'm sure many of you will just type this into your calculator. I'm going to do 180 over 3. Okay, that's going to be 60. Then times 5 would be 300. A little bit easier than doing, I suppose we could have done this. 5 times 100 is 500. 5 times 80 is 400. That's 900. Divide by 3, back down to 300. 300 degrees. Okay, 3 radians. This one doesn't have pi in it, so this one's going to be a little bit messy. So you have your 3 radians times 180 over pi. Alright, and you're just going to have to type that in, do the best you can. 3 times 180 divided by pi. It should be pretty close to 180 because 3 and pi are pretty close. And I'm getting 171.89 degrees. Alright, applications. The radian measure formula. Alright, theta equals S over R. Arc length over radius can be used to measure arc length along a circle. Okay, we're going to just rearrange it and get S by itself up top. And the arc length of your circular arc there is going to be equal to R times theta, when theta is measured in radians. Okay, so of course here for the example, they give us degrees. So 240 degrees times pi over 180. Okay, we can divide both of these by 60. That's going to reduce to 4 pi over 3 for our theta. Okay, so arc length equals radius times theta, 4 pi over 3, and we'll leave it as a fraction, 16 pi over 3 inches. 16 pi over 3 inches there. Alright, some fun ones. And when I say fun, you probably won't agree. The formula for the length of a circular arc can then be used to analyze the motion of a particle moving at a constant speed along a circular path. We have linear and angular speeds. Consider a particle moving at a constant speed along a circular arc of the radius r. If s is the length of arc traveled in time t, the linear speed v of the particle is arc length over time, or s over t. S stands for our arc length here in a lot of these. Okay. Translation. This is going to turn into circumference. Which is 2 pi r times revolutions over time, whatever your time is, minutes, seconds, whatever. So it's going to be your circumference times revolutions over time. Angular speed is then the amount, it's how fast you're rotating. It's going to be your angle divided by time, or revolutions over time. And this is in radians, so you need to change that to radians. Okay. Okay, let's see if we can do some of these. The second hand of a clock is 8 centimeters long. Find the linear speed of the tip of the second hand as it moves around the clock. Okay, so we need circumference. This is a linear speed. So we need circumference. 2 pi times 8, it's moving 16 pi centimeters every minute, right? Takes the second hand 60 seconds to get around there. So 1 minute or 1 revolution per 60 seconds. So we'll have 16 pi over 60 seconds. Type that in, delete, delete. Should be getting about 0.84 centimeters per second. So the circumference traveled there divided by time that it takes to do that one full circumference. Circular blade of a saw rotates at 2,400 revolutions per minute. Find the angular speed, so this one, angular speed in radians per second. Okay, so you have 2,400 revolutions in 1 minute. Okay, we need to change that to radians per second. So we have 2 pi radians in 1 revolution. And 1 minute per 60 seconds. So that the minutes would cancel out. So we would have 4,800 pi radians over 60 seconds. And we can reduce this. Let's not type it in yet. Let's just reduce it as far as we can to 80 pi radians per second. The blade has a radius of 4 inches. Find the linear speed of the blade tip in inches per second. Okay, so we have circumference times revolutions over our time unit. So our circumference is 2 pi times 4. Okay, that's 1 revolution. Our circumference is 1 revolution, and we're doing 2,400 revolutions per minute. So now that is, this was inches. So now we have inches over minutes. We need inches over seconds. So again, times 1 minute per 60 seconds. And that will give us 8 times that. We got 19,200 pi inches per 60 seconds. 320 pi inches per second. That's moving. That is moving. Last one, kids. Area of a sector of a circle. A sector of a circle is the region bound by 2 radii of a circle and the intercepted arc. For a circle of radius r, the area of a sector of the circle with central angle theta is a equals half times radius squared times theta when theta is measured in radians. You can then use n over 360 for degrees, I believe. Okay, for degrees, when it's measured in degrees. Okay, because that would be your piece of the pie you have there. So pi r squared would be your area of a circle, and then x degrees over 360 is going to be the piece of the circle, the fraction of the circle that you would have. A sprinkler on a golf course is set to spray water over a distance of 75 feet and rotates through an angle of 135 degrees. Find the area of the fairway watered by the sprinkler. Okay, so we have a radius of 75 feet. So I like to, if it's in degrees, I'm going to keep it in degrees. Pi times radius squared. And then we have 135 out of 360. Okay? So we got 75 squared times 135 divided by 360 times pi, 6,626.8 square feet. All right, what if we changed it to radians? So 135 times pi over 180, that would reduce to 3 pi over 4. And now we can use the other one. Half times 75 squared, not degrees, 75 squared times our 3 pi over 4. So half, we got 0.5 times 75 squared times 3 pi over 4. Ta-da! Same thing. All right, kids. There you go. We'll have the homework put up on the board for you. Do the best you can, and we'll see you on Tuesday.